Okay, so question 44. Show how each of the following compounds could be prepared using any of the any means necessary. So that means any reagent, any kind of way to tack on carbons, anything like that. You can do it in 2 steps if possible, 3, 4, 5 steps, whatever suits you the most. And usually on an exam, I'll kind of give you a little bit of a hint. I'll say this could be done in 2 steps or 3 steps or 20 steps, something like that. But here they're just kind of leaving it really short and not really giving you much of a hint. But these aren't too terribly bad. They're relatively short syntheses. So just thinking about what we have our alkyne for both of these, and what we're doing is we're actually tacking on quite a few carbons. So that's probably a good place to start. So we have triple bond, 1, 2 carbons, and then let's just start counting from the right. So 1, 2, and then we're adding on, 1, 2, 3, 4 other carbons. So this is where you may be able to work backwards, you may be able to work forwards. Either way, whichever way works for you, I'm just going to start going forward and maybe do the problem going backwards just to kind of give you my thought processes. So if you add your triple bond right here, you want to add on 1, 2, 3, 4 carbons. So this is actually a 2-step process. The first step is sodium amide. We talked about sodium amide being a base. It's going to be basic enough to deprotonate one of these carbons. Depending on how many equivalents you use, you can make this a little bit more efficient. But anyway, first step is you deprotonate this guy. You're going to end up making it negatively charged. So now, compared to before, you could have this triple bond acting as a nucleophile, but the consequence would be that you basically destroyed one of the pi bonds. You don't want to destroy one of the pi bonds, as we'll see a little bit later. But just for now, trust me on it. You don't want to destroy one of the pi bonds, and you're going to end up using we're going to end up using this particular carbon right here. Let's give it a color. So color it pink. So what we're going to do is we're going to make this guy a really good nucleophile. So this guy is a nucleophile, and now we can actually very easily tack on those other carbons that we wanted to begin with. Okay, so if we tacked on those carbons, we can add on 1, 2, 3, 4 carbons, and this is just a very basic 1, 2, 3, 4, very basic way of adding on carbons. It's just doing a substitution reaction on these halogenated alkanes. And we'll talk specifically about types of substitution in a couple of chapters, but for now, just know that this is a very generic way of doing a substitution. Okay, substitution. And what we're substituting is this carbon for the bromine. So what we have is 1, 2, 3, 1, 2, 3, 4. So we have 1, 2, 3, 4, 5, 6 total carbons, 1, 2, 3, 4, 5, 6 total carbons. So that's great. Looks like we have our carbon count right. The only thing that's missing is we need a ketone. And what we have is an alkyne. So now what you have to do is you have to remember, well, we can form ketones and we can form aldehydes from triple bonds directly. We don't have to do anything form any kind of intermediate. We don't have to go through multiple steps to get there. We can go directly from point A to point B. So what we'll do is, we have to, decide whether or not we want to, put that carbonyl compound on the, on the carbon, on the hydrocarbon, either on the terminal position, or the blue, in an anti-Markovnikov fashion, or do we want to put it on the yellow carbon in a Markovnikov fashion? So it looks like if you work your way in, this would be the terminal carbon from here, and this would be the internal carbon. So it looks like what we want to do is we want to do a Markovnikov addition. So if we want to do that, we're going to end up having to use a mercury catalyst, so mercury acetate. So that's going to be our catalyst, and then we're just going to do a sulfuric acid or strong acid, whatever, acid and water. So what we're going to end up doing is we're going to end up putting or making an enol on this yellow carbon. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so we have a reduction from the triple to the double, and we're going to end up putting that enol on the yellow carbon in a Markovnikov fashion. Okay, and so what's going to happen now is that once we have our enol, very easily and very quickly, we'll get this tautomerization that we talked about so many times. So we'll get the tautomerization over to the ketone. And voila, we're done. So 1, 2, 3, 4, 5, 6 carbons, 1, 2, 3, 4, 5, 6 carbons, and we have our ketone on the 2 position, ketone on the 2 position. So that's actually a good rule of thumb to do whenever you're doing these syntheses. Once you get the product, make sure that you've added the appropriate number of carbons, make sure that you have your functional groups in the right space, because these little things make a huge difference in terms of, whether or not you get partial credit or no credit. Okay. So overall, not too bad. 1, 2, 3 stepper, depending on how you want to, define what is a step. But anyway, well, for all intents and purposes, we did this in 3 steps. Okay. So now we're going to do the exact same thing. We're going to, look at the products for this sub question C and see how it's different from, the starting material. So here we have a hydrocarbon, 1, 2, 3, 4, 5 carbons long versus 2. So first things first, we know we're going to have to end up adding carbons. And for all intents and purposes, for what you know, the only starting material that you can really use to tack on carbons is this triple bond, for now at least. So whenever you find out that you have to tack on carbons, you need to do it on the triple bond before you affect it to get something else. Because again, we need to make sure that what we use, the base, to actually deprotonate this alkyne to make it nucleophilic is going to be strong enough. And you have to start thinking about pKa's of the alkyne versus the alkene versus alkene. And as you go down this line, you get way more difficult or have a way more difficult time of trying to deprotonate. So with a pKa of 25, the sodium amide is perfect to deprotonate this alkyne. But anyway, tangent. Okay, so first things first, let's go ahead and tack on our carbons. So we know 1, 2, 3, 4, 5, 1, 2, so we need to add on 3 different carbons to make a total of 5. And again, we can do this in 2 steps, sodium amide, and I'm just going to combine these 2 steps into one here, and just to save a little bit of time and energy. So we need to add 1, 2, 3 different carbons, so we have a total count of 1, 2, 3, 4, 5 carbons to match this guy up. Okay, so what we'll get is we'll keep our triple bond, 1, 2, 3, and now we have the setting to get this guy on the right. Okay, so now this is almost identical to the one above. It looks like you could potentially try to reduce this alkyne directly to the alcohol, but keep in mind if we do that, then we're going to get that tautomerization. So the easy way to bypass this, if we actually do want the alcohol, is we can also hydrate an alkene and not the alkyne. Because if we hydrate the alkyne, we're going to get some kind of tautomerization going on, and we're going to lose any OH carbon-oxygen single bond. So the way to prevent that, very, very simply, is just to reduce it, not to the away from the alkyne. So we can try to reduce it a little bit or a lot. And if you say, well, what if we added H2 palladium on carbon? If you did that, you would definitely reduce it, but you would reduce it all the way down, 1, 2, 3, 4, 5, all the way down to the alkene. And once you have the alkene, you're kind of SOL. So this is no good. Okay, so what we're going to have to do is something a little bit different. So we're going to reduce it, but we're not going to reduce it all the way. We're actually going to do a slight variant, H2, and let's say for my case, I'm just going to choose Lindlar as a catalyst. So again, remember Lindlar is a poisoned version of this, and we're going to end up forming an alkene instead of an alkane. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so now that we have our alkene, we can hydrate directly and not have to worry about any kind of tautomerization going on. And we also know that if we number this 1, 2, we know we want to hydrate at the 2 position, which is going to be the Markovnikov position. So what we're going to do is not use any hydroboration steps. We're just going to do an acid catalyzed hydration. So just H plus from sulfuric acid or any other kind of strong acid in a catalytic fashion and water. And so what we'll end up doing, 2, 3, 4, 5, is we'll end up hydrating at the 2 position. And this molecule is that molecule. So again, not too terribly difficult. There's one little roadblock mistake that you could make. But overall, 1, 2, 3, 4 steps. Not too bad. So this bottom one was 4 steps, pretty easy. This one up top was even easier, done in 3 steps. So this is pretty darn easy. All right. Okay, next question.